All right. So this is the accuracy story. The only thing we've got left to talk about is stability. All right? So there's two key issues. Accuracy, stability. Every scheme has to evaluate this. Every time you solve something in the computer, you better be aware of your accuracy. Because you're at a conference, let's say, and you've got this nice result that you're presenting, and somebody in the audience, maybe they're a big shot, says, hey, how accurate are those results? Do you know if you can? You better have an answer. Okay? You're now gearing up for that, and you better have an answer. You better know what your accuracy is, how good your error, how good your prediction. These things matter. Okay? And once you test bed it and understand it, then you can start thinking about having confidence in your scheme to make, let's say, bigger predictions for your science or whatever you're doing. Okay, so let's talk about stability. And there would be nothing worse than writing a paper with wrong results. Because then it's just bad. And then you hope nobody really reads your paper. Except for your mom. And your mom will never know. Oh, yeah, that's right, Mom. Come on, you just don't know math. Okay. All right, so let's talk about stability. Start off with a simple differential equation to talk about it in the context of here, which is dy dt is equal to lambda y. With some initial condition, let's say at time 0, it's y naught. Simplest differential equation you can write down. It has a very simple solution. Y of t is equal to y naught e to the lambda t. Okay, so we're going to think about stability and setting up an Euler scheme in the context of this and to see what happens. Okay, so what is the Euler scheme? If we have this, the Euler scheme said, you know what you do is you say, my solution in the future is what it is right now plus a little bit of something. My f here is just lambda y. So I can replace that f with lambda y of n. Then I have a y and y of n. I can take those out. I have 1 plus lambda delta t y of n. This is a very nice iteration procedure, by the way, because notice what happens. If I put in y0, my initial condition, right? So this is my initial condition, y0, to start the iteration process. Then y1 is equal to 1 plus lambda delta t y0. And then if I have y2, well, I just multiply by that again. And then y3, I just multiply by that again. So if I take n steps into the future, right? So let's take capital N steps into the future. All I got to do, take this number here and raise it to the nth power. Okay. Now, you know that when you evaluate y naught, you're going to make a round-off error, right? So it's not going to be clean. It's going to be almost. It's going to be 10 to the minus 16 error, but still, you ask the following question. What happens if I keep iterating on this thing? As n goes to infinity. In other words, I just iterate for a long, long time. What will happen to this thing? Okay, so first of all, let's look at the error. So y naught is going to have some evaluation of the function itself plus some round off. So my error is also going to look like this. Now, here's a bad thing to happen. Error goes to infinity. I think, that's normally anybody would say, yeah, if an error goes to infinity, that kind of is probably bad, right? Part of what you would like to do is not have errors going to infinity. But here, you see that if n goes to infinity, this is really important. You're just raising a thing. And by the way, if that's bigger than 0, and presumably you're taking delta t to be a positive number, so if you have lambda, which is positive, what happens to this number here? That thing goes to infinity. Okay? That's problematic. That's where we start having the idea of the unstable scheme. Okay? Part of what you want to do is control the error in any scheme. Now, it turns out this is a peculiar situation here with this specific model. And the reason is, what's also happening to the solution? Solution in time goes to infinity is also going to infinity. Okay? For lambda positive and real. Okay? All right. So you might say, well, my solution's going to infinity, and I add infinity plus infinity. You don't get to infinity. You still get infinity. So I still got the right answer. Right? Okay? I love doing math with infinity. There's all kinds of cool things you can do with it. But here, this is bad. So that's one thing we can think about. In fact, it sets up something that we want to really think about is if this thing is actually negative, you know, let's say it's negative 0.1, and there's some small delta t, then this is below 1, right? If this thing here makes 1 plus something a little bit negative, then it's below 1. If you take something below 1 and you just keep raising it to the nth power infinity times, what happens? It goes to 0. I love that. I love error going to 0. Okay, it's totally unrealistic. But we always can dream of the errors going to 0. So we have these two cases that are of interest here. If we look at the absolute value of that thing, if that thing is less than 1, then error goes to 0. If the absolute value of the thing, now we're considering, instead of real lambdas, we can have complex lambdas. Lambda can be some complex number, imaginary number, and we have these two cases. And here's how we think about schemes. This is stable, that's unstable. We will play around with this later in class. Instability of schemes. If a scheme is unstable, as I said, it will announce itself to you. It will not hide behind something and go, I don't want to tell them I'm unstable. No, it'll just make your computer go to NANs and solutions go to infinity, and you'll go like, that doesn't really make sense at all. Okay, so that's a condition.